it is better. Yes, thank you very much. And thank you very much, the organizing committee and Professor Effie Cartini for the invitation. It's my pleasure. As I was introduced that my specialty is to use neutron scattering for research. And yes, just let me make the full screen so we know. Do you see my presentation?
Yes. Yeah.
Okay. So I'm coming from Helmholtz Zentrum Berlin, which was grounded in 2009 as a merge of two institutions. The former Hahn-Meitner Institute was quite famous in solid state research using neutrons and basis synchrotron. We have the two scientific campuses, one in Berlin, in Wannsee, it is former West Berlin, and one in the former East Berlin. And we have right now the particular focus on research on energy, including solar energy, chemical energy storage, quantum and functional materials at photoscience. The HCB at the time employs about 1,000 employees. I'm working as a part of a department for electrochemical energy storage, which is very close to the research area of Professor Dr. Cartini. So we do different kinds of the batteries, in particular solid state batteries. There's a big laboratories grounded. And my particular laboratory is to use neutrons to investigate storage processes in porous materials. And we have also
berbagai jenis sumber daya alam yang melimpah.
yeah, very sorry for this. So Mrs. Rita has a problem with the computer, actually, yeah, computer problem, not only with the internet. Ah,
Yeah, it is.
okay, Rita.
Something is like it's usually stable, but something is happening to the network and it's break completely down. So do you see my presentation? Do you see my presentation or not yet?
Not yet.
Okay, then let me share that again, and then I will start.
You can also send to us whenever a problem, so we can help. Yeah.
Okay, so let's go quickly then. We don't have much time. So I am working with neutrons, and the neutrons work very, very simple. So the neutrons are basically particle in the wave, and if they interact, they scatters from the particles or from some kind of the system, that they can change the energy and they can change the wavelengths, and they can provide in this way the information either about the structure or the motion of the system. So basically on what you study or analyze in your system, this is, you can study the specific details of your structure. For instance, if you are looking for just transmitted neutrons, like a picture, you can make a tomography. Or if you are looking for some kind of change of the wavelengths, which can be modified by the change by the structural characteristic of your system, then you can study the structure. And if you can add the discrimination of the energy of incoming and outgoing neutrons, then it gives you the information about the motion of the atoms or ions in your system. So the neutrons has a very sensitive to the hydrogen and lithium, by the way. It is much more sensitive than the X-rays. And in the same time, they can access a very big domain in space and time compared to the other methods, and which makes these methods particularly interesting in the time when the entire modern technology is based on molecular engineering. So you do need to know how the molecules move. And for this type of engineering, you need some kind of information, a particular time and space domain, and exactly this domain is covered by neutrons. This is what makes them interesting. So the broad of phenomena, what you can study with this method is very broad. You can study molecular vibrations like in Raman, for instance, but you can move lower in energy and look for the collective vibration, phono-like modes, also transport properties like a diffusion, and which is also quite interesting and particularly important for the ionic conducting system. So the instruments are quite big, actually, in neutrons. You see here the part of the instruments here, particularly this is the detector chamber of our instrument, and you see it is about 8 meter diameter and 5 diameter high. These big parts you really need to detect very, very tiny, you see, tiny materials. This is our samples. So you design this big infrastructure using neutrons with making the very intense beam and then focus it on these small parts. This is what we have right now, is actually 4 milligram of electrolyte confined in 70 milligram of porous carbon. So the 70 milligram of porous carbon, this is actually background, but what we are looking at, it's 4 milligram. And these amount of materials are very important, because if in the past you would need about 1 gram of materials, which if you are working with modern novel materials is not always easy to synthesize. So going from 1 gram to 4 milligram is already a big change and makes this methodic already comparable with synchrotron, for instance, where you also use tiny amounts. So as I told, that neutrons can have, based on what you focus on your analysis of scattering neutrons, you can have different techniques. For instance, as I told, tomography is very heavily applied for the energy research. For instance, here our station at Helmholtz Zentrum Berlin was used for the investigation of distribution of lithium ions in batteries. Then you can apply neutron diffraction. For the porous materials, it's particularly interesting if you're looking for something hydrogen containing. And if you're doing particularly in situ, you can define the places where the atoms are or molecules are inside these pores. Then you can use also the small angle scattering. This I will tell later in my example, to investigate pore size and shape. And of course, you can use a neutron spectroscopy to see how the molecules or atoms or ions are moving inside these pores. So as I told, that our research focus is, my research focus is investigation of the porous materials. And if you're confining something porous material like gases and liquids, and the porous materials are very well known in the nature. Even we are basically consisting from porous materials. Our lungs are porous materials. Our brain is porous materials. The novel modern materials have right now synthesized with very high surface areas, with low density, and they can be synthesized with very tunable hierarchical structures. So basically, you can tailor really pores for your use. And if you are using the porous materials for the confinement of something like ions or the gases and liquids, of course, this intake characterized by these macroscopic properties. For instance, for gases and liquids, you usually measure the intake at some particular temperature, it calls isotherms, or for the, for instance, ionic storage, you usually measure this capacitance and voltage curve and see how it is, how the ions can be how it is reacting, charge and discharge curves are reacting, and how it is working in this system. So what do you want to know if you're looking for the porous materials? Of course, you do need to know how the pore, what is the pore size, but also is important the pore shape. What is the nanomechanical mechanism behind this intake, what we see here? How the ions or molecules enter the pore, where do they stay, where do they position themselves, and what are the different stages of this intake? And of course, what you want to know is what is a transport, how do they move there, what is the diffusion inside the pore, and how stable these processes are, what are the guest-host interaction. And this particular question we try to address in our research. So starting with the first one, how to establish the pore size and shape, and how we can use the neutron scattering. For this, I would like to demonstrate on this example, which was done. This is a joint study with the University of Tartu, which was dedicated on investigation the pore in the metal-derived carbon materials, which are novel materials synthesized for different type of application, in particular for the electrochemical storage. And the materials, these materials are using is a metal carbonate, and you derive this metal carbonate by letting the chloride gas going through these materials at very high temperatures. So you're kind of gating these metals out and creating the pore inside. And this pore depends on what kind of metal do you have inside there. And University of Tartu synthesized broad range of the metal carbide materials. You see here the titanium, silicium, and molybdenum. And if you're using these common techniques like volumetric absorption techniques, you can establish some kind of the pore size. And you see here, there are usually two peaks are showing what are here and or here. And they are usually, the people, I think that this is what is the different size of the pores. So you have the small pores and then you have the large pores. So you can establish with these methods also the volume, try to establish volume and specific area. What can you do with neutrons there? What we wanted to do with neutrons to establish it more in details and to establish this, the size and the shape. And what we have done here, that you can feel this small angle technique, usually getting the curves like that, yes, which is the response to this density correlation, what you use, what you see there. But what you can done also in addition is to fill the pores gradually by putting some kind of materials which has the same scattering length as a carbon. And in our case, it's water. So you putting the water inside and closing some of the pores down, or the gradual closing down of the pores. And in this way, you can look for the signal, how it is changed with the amount of water, and establish your signal, establish the size of the response much more precisely. And using this contrast matching technique, we could establish that actually the pores are not the slit-like pores, which are characterized only by one pore size, but what was done in the past. But what we deal with, it is a complex 3D pore size. In only simple system, we do have this molybdenum mesoporous system, we have the slit size shapes. But in the small ultra porous system like titanium and silicium carbonate, we do have a spherical and cylindrical pores. And they do have actually not only one size characteristical by two. So they have the width and the length. And exactly these numbers are reflected in these peaks in here. So what we have here, this is two characteristic numbers which are reflecting the pore size. And this information you can get only from this contrast matching technique, not from other methods. And so once you establish this pore size, you want to know what is happening actually in pore itself. Yes, how the ions are moving and how molecules are moving inside the cages. And this is, of course, a very complex question, because you can switch on the guest-host interaction, and this guest-host interaction depends on the chemistry of your system. But what is a really geometrical impact? And for this purpose, we took some kind of a particular system which consists from the porous ice and place the hydrogen in there. And this porous ice creates the two cages in there. And we do not, the advantage of this system is that we do not have an interaction between the ice and the hydrogen. So what we have here, by looking how the hydrogen move inside the cage, we can look and establish the potential, which is potential landscape of this cage, which was created really by the cage geometry and size. And by looking this dynamic motion of the hydrogen, we can really kind of map this landscape in there. And for this purpose, we used neutron spectroscopy. The signal in there is described by this complex formula, basically the sum of the Lorentzians. And what is important here, this Lorentzian provide us the information about the diffusion. But we have also another factor which describes as geometrical fingerprint of this diffusion. So if diffusion is happening through some kind of position which remain the same in time, they will have some kind of geometrical shape, then it will be reflected in this factor. And it turned out, so you see here the hydrogen itself, the bulk hydrogen. So you see at 10 Kelvin, we do not see any signal. And at 20 Kelvin already it's melted, and we do see a broad Lorentzian in there. But when we place the hydrogen in the small cage, we see that it remains frozen at temperatures as high as 50 Kelvin. And they're placing the hydrogen in the large cage, we see completely opposite. So the hydrogen, why it disappeared again? Sorry. I hope it is not. Yeah, okay, so it's working. So we see here that it is moving here at 10 Kelvin when the bulk hydrogen is frozen. So you see completely different dynamic responses, but just only slightly increasing or decreasing the cage size. You either localize the hydrogen or delocalize the hydrogen. And this is exactly what we're talking is due to this landscape shape. And you can analyze this landscape shape by looking exactly this analyze of this factor which describes the geometry of this motion. And it turned out that in small cage, exactly, we have the confirmation that this hydrogen itself is localized within the center, within this very, very small sphere, which results, which radius is relatively small, even at temperatures as high as 150 Kelvin, while in the large cage where the hydrogen is moving between the 4 tetrahedrically shaped positions, and this is how the landscape is. This is exactly due to potential minima to potential landscape. So this gives you the configuration of this minima, which is defined by the geometry of this cage, and where these molecules or ions can be. Interesting is that to place the hydrogen, this localization, this landscape with a deep minimum inside the cage, working like a molecular pump, to place hydrogen in there, you need 200 bar, but to place hydrogen in the large cage with a flat potential, you need 2000 bar. So basically the confinement works a kind of effect like a pressure. It allows you to put the molecules inside there and remain there much more stable at much more high temperatures. Okay, the same effect we also see, we can use this effect for this microporosity and size shape for the storage effect. For instance, we looked also for the diffusion. I think I have to place it in here because you won't see. Yeah, we looked for the diffusion of hydrogen and this in this microporous metal-derived carbon, where the pores were defined of different shapes, and we found that the best diffusion you see here. This is the best smallest diffusion coefficient we see in the pores with a sphere size, and then slightly increasing with the cylinder. So the cylinder is also quite good, keeping the molecules in there and the sphere. But when you are increasing and going to the slit-like, we see the quite high increase of the diffusion, jump-like increase of the diffusion, and the storage effect is much less. Okay, then when we are looking again for this porous materials, we are interested to know how these pores are filled. So we do have this kind of the hysteresis, but where is actually the molecules are going inside these materials? And to understand that, we investigate water in the zeolite system, which is a really simple one, which built some kind of these one-dimensional channels with about 8 angstrom diameter. And consider that our water can be described by the molecules of about 3 angstrom radius. You see that in 8 angstrom, you can fit mostly only 2 molecules of water side by side. So it's not much more. So this is kind of relatively simple system, and we wanted to know how water fills these places. And we applied a neutron diffraction to investigate where the water is, and also the X-ray diffraction to see whether we see the changes between the framework itself. Originally, this system is described as a hydrophobic system, so we do not see really the chemical bond formation between the water and the zeolite. However, still we do see quite interactions in there. So first, what we have found out by application of diffraction, there are basically two stages to fill, stages of this filling process. In this first stage,
audience, sorry for the audience that yeah, it's happened again that Dr. Rita have also another problem, technical problem. Yeah.
There is something.
Okay, are you there? Okay.
Yeah.
Rita, can you speed up? Yeah, okay, please.
It is something is happening with the network, and this is what
Okay.
the sending entire system to crash. I send you the presentation, so
Okay.
in the case if I crash again, you can
Okay.
finish it for me.
Okay, so I have the, okay, good. Okay, Sinta. Yeah,
Filling
please.
up. So basically, when the pores are filling up, and this is what we see in the water system, and also later for the hydrogen, the molecules are first going to the walls, to close to the walls, and then only afterwards going to the, when this position around the walls are filled, then they're going around the center. And interesting thing is that by this interacting with that, they can have, even in systems which are hydrophobic and guest host interactions originally, ideally, should be switched off. Even in such system, we do see the interactions. And these, in our case, and they're depending on the pore geometry or how the pores are. In our case, since we do see some kind of one-dimensional channels, in our case, the dimensional channels becoming smaller, again, deforming this potential landscape inside the cage and facilitating even the stronger intake of water. But first, as I told, they're forming some kind of immobile water molecules around the walls, and then more mobile water molecules if the molecules are is entering the center. And the same effect we do see also for the hydrogen. So if we place the hydrogen in this molybdenum carbon CDC, which has a mesopores, in there we do see first formation of immobile hydrogen around the walls, and this is reflected in relatively low diffusion coefficient. And once these positions are filled, the hydrogen is going inside the pore, and we see already jump like the increase of the diffusion coefficient is starting to be more mobile, and this is really moving more faster. So how can you use this guest host interaction for our purposes? And this is quite interesting. This is our another study in, I have not in modus, sorry. So this is what I would like to show. Another example, it is when we place a hydrogen in metallic organic framework. This is a study which is running in collaboration with Professor Oh from Korea. And this MIL53 is quite famous metallic organic framework. And it can have pores which are quite flexible, which can open and close if you change the temperature or you place some kind of materials in there. What was surprising, however, that if you place the hydrogen and deuterium in there, the pores react differently. So if, for instance, for the hydrogen, so they can open or close, but you see here already on the shape of the isotherms that at 25 Kelvin, we see completely different intake, much higher as for hydrogen. And this effect disappear at 40 Kelvin and then start again, we do see completely different behavior at 60 Kelvin. So, and the idea was that we can use some kind for the, as a sieving material to select the hydrogen and deuterium isotopes, which is actually quite costly and complicated procedure currently in the industry. And you need H2ND2, particularly for the medical purposes. And if you can increase selectivity and do it at a relatively moderate temperature, this has an enormous impact for industrial applications. So how to investigate that? This is what we applied neutron scattering spectroscopy and look for the diffusion, because these isotherms are governed by the diffusion of your element inside the pores. And we looked for the diffusion of the hydrogen and deuterium inside the pore. You see the signal. Again, we applied this Lorentzian fitting in there, and then look how the vis of the Lorentzian propagates in space. And this you can establish from the diffusion coefficient. And you see here that at 25 Kelvin, we do not see quite differences, basically due to the low background. At 40 Kelvin, we do not see differences, but these differences appear at 60 and 77 Kelvin. These are clear differences in the width of our signal. And this established allow us to establish a diffusion coefficient and see that diffusion, the propagation of the hydrogen and propagation of deuterium inside these materials is a completely different, and really quantify these materials or allow to use these materials for the quantum sieving and isotope separation.
Dr. Rita,
yeah.
The time is 3 minutes left.
Then I would probably show the last example of this hydrogen.
Okay.
So another very interesting example was that if we are placing again the hydrogen in these carbon materials, you can create these carbon materials which has mesopores but consisting from some kind of microcavities like that. And if you localize hydrogen in there, becoming confined and creating localized diffusion in there, and this is again like a pressure effect on the walls. And as a result of this, you can exercise this local pressure, and this leads to the graphitization of the carbon, such system as a carbon. As a result, we see this kind of first order transition, structural transition from amorphous to carbon, which is very reversible. So it's happening at some particular temperature, at some particular pressure of hydrogen, and then carbon becoming amorphous again. I think this kind of very interesting effect, I didn't see it before, can justify application of these materials for some kind of isotopes. Okay, so I would like to finish that here.